my name is Julia James, and this is my Physics 2212 Revisited Charged Tape Lab. Starting off, I would like to outline the purpose of this lab and some important physics principles that help to explain the theory behind the lab results and calculations. The purpose of this lab was to prepare charged pieces of Scotch tape and observe their interactions to determine approximately how much excess charge can be found on one piece of clear tape. For part 2, instead of assuming that the electric force acts as a point charge, we assume that the charge is distributed evenly across the pieces of tape in the computational result. I then compared this result with lab 1. For part 1 of the lab, I first performed the real in-person lab with my GPS group and took observations and created a computational model using code and glow script to plot the gravitational and electrostatic forces to predict the number of deficient electrons. For part 2, I created a new computational model with the assumption that the charges are evenly distributed. At the conclusion of Lab 1, results showed that there was a positive charge on the tape, creating a repulsive force between the two tapes when they were held near each other. There was a predicted charge on the single tape of 3.94 times 10 to the negative 9th coulombs. However, through the different method of Lab 2, the new predicted charge for the single piece of tape was found to be 1.29 times 10 to the negative 9th coulombs. The first important physics principle to note is Newton's second law. This identifies that the acceleration of an object is dependent upon the net force acting upon a body and the mass of the given body, and it allows us to set the gravitational force equal to the electrostatic force. Another important physics principle is gravitational force, which is the force that attracts any two objects with mass. The force of gravity on Earth is 9.8 meters per second squared, and we calculate the gravitational force in this lab by taking the mass of the tape times this number, as shown below. Our final physics principle of focus is Coulomb's law, which allows us to calculate the electrostatic force between two charged particles. The force is attractive if the two charges are opposite signs, while the force is repulsive if the charges have the same sign. Coulomb's law is described by the equation below, and from it we can derive the bottom equation, which calculates the electric force over a line charge, which can be used repeatedly to act as an integral and calculate evenly distributed charge. For this lab, the system is tape B, which is the tape that is suspended between two objects, while the surroundings are tape A, which is the held tape, and Earth. Tape B is the system because we are focusing on how the forces of tape A and Earth act upon it. For this lab, I operated under the assumption that air resistance is negligible, both tapes have approximately the same charges, and that charge is equally distributed along each line length of tape. To add charge to the tape strips, we stuck two pieces of tape together and ripped them apart. This process is represented below. This diagram represents the system and surroundings discussed in the previous slide, with tape B being the suspended tape piece and tape A being the held tape. As you can see, there's an electrostatic force acting upwards on tape B, while the gravitational force acts downwards. However, in comparison to the previous lab, where the electrostatic force acts as a point charge, the total electrostatic force is actually the sum of the various line charges throughout the piece of tape. At the moment when these forces hit equilibrium, there is a 0.01 meter distance between the two tape pieces. This video represents what occurred when the two charged tapes were held near each other. As you can see, there's repulsion present, meaning that the charges of the tapes had the same sign. I will not fully run through the calculations to predict the point charge in the piece of tape, as that was the purpose of Lab 1, but all relevant calculations are shown on this slide. Moving on to the computational model, I first identified all the initial conditions, including Coulomb's electrostatic constant, the acceleration due to gravity near Earth's surface, and all relevant tape information for experimental calculations. I also included the number of point line segments I wanted to calculate for, to act as an integral, and the estimated net charge of a piece of charged tape. For the next part of the code, I defined the calculations for the electric field and the line charge, as shown on the slide. I did this by inputting relevant equations such as the ones identified in the introduction. This last part of the code highlights the loop in which the electric force on each segment of tape is calculated and added together through the superposition principle in order to find the total electric force on tape B. The left image shows my initial resulting computational model, which is found when my charge input of 3.94 times 10 to the negative 9th coulombs from part 1 of the lab is used. As you can see, the magnitude of the gravitational force is far greater than that of the electric force, proving that the point charge method may not be the most accurate way of calculating the charge of the tape. I then performed some calculations, as shown on the slide, to calculate the charge of the piece of tape using the line charge equation, which when added repeatedly acts as an integral and represents a distributed charge. I found that this charge was equal to 1.29 times 10 to the negative 8th coulombs. As you can see, this balanced the gravitational and electric forces out, proving the calculated magnitude of 1.489 times 10 to the negative 3rd newtons for the electric force. As you can see by the values shown, there was a difference of 8.96 times 10 to the negative 9th coulombs when calculating charge using the point charge versus distributed charge method. This lends itself to the conclusion that identifying when something is a point charge versus distributed charge is important for accurately predicting charge. Some sources of error in this lab could be that each piece of tape was not 100% equal in charge, and that charge may not have been totally equally distributed. These sources of error could lead to differences in real-world versus computational results. Finally, I will discuss some follow-up questions and how they relate to previously discussed physics principles. For the first question, if I had modeled each of the tapes as single-point charges, the charge would have been the same as in the first lab, and the magnitude of the electric force would have been significantly less. This idea is represented by the models shown earlier in the presentation. For the second question, these estimates differ because the point charge model calculates for only one simple electric field, whereas the line model / distributed charge model requires a summation of multiple fields. The line charge model is likely more accurate because charges are more distributed in reality, and this is shown through the computational models as the magnitude of electric force calculated by the line charge model is closer to the magnitude of the gravitational force. This concludes my physics charge tape lab. Thank you.